Hello and welcome to this lecture on machine learning. In this lecture, I will walk you through key concepts of machine learning using animation, code, and examples to help you build the underlying intuition and get ready to write your first machine learning program. So let's get us started with an example. Suppose a student is studying hard for an exam. The more he or she studies, the better the score is likely to be. This reflects the core of machine learning, discovering patterns in data. Now let's look at a small data set of 10 students. For each student, we know how many hours they studied and what score they received. Please keep it in mind that this lecture is intended to give you the underlying intuition behind machine learning and that having only a few data points in the dataset is not sufficient for real-world applications. So this is a very simplified example to show how machine learning works. Here, the study hours is the independent variable. This is what we use to make predictions. The score is the dependent variable because it depends on how much the student studied. In machine learning, our goal is to find a relationship between these variables so we can predict future scores based on the study hours. Let's pause for a quick explanation. Imagine a light bulb and a switch. The switch is the independent variable. We can turn it off or turn it on. The light bulb is the dependent variable. It depends on the switch. If we flip the switch, the light changes, but the light doesn't control the switch. What happens to the light has no effect on the switch itself, just like that. In our example, the number of hours studied is the switch, the independent variable, and the exam score is the light, the dependent variable that responds. So in machine learning, we study how inputs affect outputs. Now let's bring the dataset into Python to see machine learning in action. First, we import the linear regression model from the powerful scikit-learn library. This will help us find the best fit line for our data. If you're unsure about what exactly a library is, I highly recommend you watch the course on introducing libraries. Also, I have another course that explains how the best fit line works, which can significantly help you understand the intuition behind it and see how regression works. Next, we import the R-squared score metric, which tells us how well our model explains the variation in the data. Next, we have hours and scores. Notice that hours are written inside double brackets, while scores use single brackets. Because scikit-learn insists that your feature matrix X must be two-dimensional, whereas your target vector Y is one-dimensional. Let's pause for a moment to see why we have inner brackets here. Each inner list represents one student, so this is one sample. Inside that inner list, each value is one feature. Right now, there is just one feature, hours studied, so you see that. But if you want to add another feature, say age, you would simply stretch each row to hold two values. In that case, you can assign any variable name you like. Now, you know double brackets naturally group all features for each student into one row, exactly what scikit-learn expects. Meanwhile, your dependent variable stays a simple list of numbers, one per student. Now, let's move on and split our dataset into training and testing sets. We will use 80% of the data for training and the remaining 20% for testing by slicing up the first 8 entries for training and the last 2 for testing. We ensure the model learns from the majority of the data and is then evaluated on the unseen examples. So we generate our test set using the final 20% of the data. We take hours from index 8 onward to grab the last 2 feature rows, and we take scores from index 8 onward to grab the last 2 target values. These two samples in X test and their corresponding Y test scores are kept completely separate from training. Later, we will use them to evaluate how well our model generalizes to new unseen data. Therefore, this part is completely hidden from our model during training. In the next step, we create an instance of the linear regression. Think of this as a learner ready to analyze data and assigning it a variable named model. This gives us a fresh regression learner source from scikit-learn that is ready to be trained on our data. Now let's go to the next step. At this moment, our model grabs the feature matrix X train and the target vector Y train and searches for the pattern that best explains how hours studied, which is independent variable, relates to a score, which is dependent variable. This step is the most crucial in the training process as the model tries to learn the relationship between inputs and outputs by minimizing the error in its predictions. For further information, you can also refer to the course on regression to see how a model works in more detail. Now that our model has learned the relationship between hours studied and scores, we move on to make predictions. We give the model unseen data, which is X test here, and since the model has learned from the training data, it tries to make predictions based on that knowledge. The model uses the pattern it discovered during training to output its predicted scores, which we store in ypred. Now the predictions ypred can be compared against the actual data, which is ytest here, to evaluate how well our model generalizes. So we evaluate the model's accuracy on our test set. This takes in our actual test target, which is ytest here, and our predicted values, which is ypred, and returns our squared score. And let's have a quick pause and check how accuracy score works. We have the list of actual data and predicted data. R squared equals 1 minus the residual sum of squares divided by the total sum of squares. But what does that actually mean? First, the residual sum of squares is the total of all the square differences between the actual values and the values predicted by our model. Then we have the total sum of squares, which measures how far the actual values are from the average of all values. Let's start by understanding this metric step by step. I would like to first calculate the mean of y-test. Next, we calculate the total sum of squares, which measures how far the actual values deviate from the mean. It represents the total variation in the dataset before any modeling. And then we should calculate sum of the squares of residuals. This is the difference between the actual values and the predicted values. And this shows how much error our model is making. With both the sum of the squares of residuals and the total sum of the squares calculated, we can now compute the R-squared metric. Here, the R-squared value is 0.58. The closer this score is to 1, the more accurate our predictions are. In other words, the closer the R-squared value is to 1, the better the model fits the data. Here, the R-squared is 0.58. This means that approximately 58% of the variation in the actual scores can be explained by the number of hours studied. The remaining 42% is due to other factors not captured by the model. But keep in mind, this example only had 10 data points, which is extremely limited. With such a small dataset, the model has very little information to learn from and may struggle to accurately capture the true relationship between study hours and scores. I hope you found this lecture helpful. Thank you for watching and feel free to share your thoughts to help improve further lessons.